We've talked about where electricity comes from. Now we're going to look at some basic electrical quantities: current, voltage, and resistance. These three are all related. The law that defines exactly how they're related is called Ohm's law, and we'll review how that works too. The last two things we'll go over are electrical power, energy, and the units of measure that apply to them: watts and watt-hours. We'll begin with what current is. It's the flow of electrons. Current is measured in amperes. An ampere is actually a rate of flow of electrons. The rate of flow, or amperage, is important when you're discussing current, and so is the direction of the flow. Direct current flows in only one direction, pretty much like the flow of water through a piping system. Alternating current is different. It flows back and forth. In AC, current flow starts in one direction, stops, and reverses itself continually. We're going to use direct current to explain most of the concepts in this review. You'll find that when you're dealing with alternating current, the rules still hold, but the characteristics of AC require some minor variations in their application. Voltage is the next quantity on our list. It's the driving force that makes electrons flow. Its unit of measurement is the volt. A voltage source works a lot like the pump in a piping system. The voltage source pushes electrons through a wire pretty much the same way a pump pushes water through a pipe. A couple of common voltage sources are batteries and generators. Resistance is just the opposite. It opposes the flow of electrons. When you're measuring resistance, what you're actually measuring is just how difficult it is to push electrons through something. Resistance is measured in units called ohms. Now, all matter offers some resistance to electron flow. If it offers a great deal of resistance, it's called an insulator. But if a material offers very little resistance to flow, it's called a conductor. The unit of resistance was named for George Simon Ohm to reflect his discovery of the relationship between current, voltage, and resistance. He said 1 ampere of current will flow if there's 1 volt of driving force and 1 unit of resistance. The unit of resistance was named ohm. Ohm's law states in general terms exactly how the relationship between the three works. Current is equal to voltage divided by resistance. Using the symbols I for current, E for voltage, and R for resistance, it looks like this: I equals E over R. You'll know Ohm's law like the back of your hand after a while. It's useful in all sorts of situations because it helps you to do two important things. First of all, it lets you figure out one missing quantity in a circuit if you've got the other two. And second, it gives you an idea of what's going to happen in a circuit if one of the quantities changes. You'll see what I mean in a minute. We're going to begin by using it to figure out the missing quantity in a simple circuit. This one's about as simple as they get. It's only got 3 components: a battery, a switch, and a light bulb. The 3 components make up a circuit because the wires that connect everything together form a continuous loop. In plain English, a circuit is just a path for electron flow. This circuit provides a path from the battery through the switch and the light bulb back to the battery. If we know what the voltage and resistance in this circuit are, we can use Ohm's law to figure out what the current is. To find out what the voltage and resistance are, you might measure them with a meter, or the values might be printed right on the component. Just for the record, we know the values of voltage and resistance in this circuit because the battery's got it printed right on the casing. And we measured the resistance of the light bulb and got 24 ohms. By the way, the bulb doesn't offer the only resistance in this circuit. There's additional resistance in the wires and the switch. That's because any material offers some, but the additional amount of resistance is so small we can ignore it. Okay, first we're going to use Ohm's law to determine current. I equals E over R. I is the unknown. E equals 12 volts, and R equals 24 ohms. 12 divided by 24 equals 0.5 amps. So, thanks to ohm, we know we've got half an amp flowing through this circuit. And we didn't have to pull out an ammeter to measure it. Now let's solve for resistance. To do that, we'll rearrange Ohm's law to read R equals E over I. We need to know the values for voltage and current in order to do that. Here's a schematic that represents a circuit just like the one we just saw. Only this time the circuit contains a 6-volt battery, and there's 1 amp flowing through it. R equals 6 over 1. That means the resistance in the circuit is 6 ohms. We'll manipulate the formula again to solve for voltage. E equals I times R. Let's say current is still 1 amp and resistance is 9 ohms. E equals 1 times 9. The battery in the circuit's got to be 9 volts. Well, that's how you solve for one quantity if you know 2 out of 3. Now, you can also use Ohm's law to predict what will happen in a circuit. This circle represents the relationship between current, voltage, and resistance as stated in Ohm's law. If voltage remains constant, but resistance decreases, then current has to increase. This is what happens when a circuit's shorted. The short lowers the resistance in the circuit, and the current goes up. If it goes up high enough, the wiring burns. Now, let's think about it the other way around. If voltage remains constant and resistance increases, then current's got to decrease. The greater the resistance, the smaller the current. If resistance gets high enough, there's no current flow. When I put this switch in the open position, the resistance in the circuit is so great, there's no current flow at all. When you're doing a repair, you'll find you use Ohm's law without even realizing it. For instance, if the resistance is extremely low, you'll know that the circuit is shorted, and you'll take steps to find out why. Well, that takes care of current, voltage, and resistance. But there are a couple of other things we need to mention before we're through. Power and energy, and the units they're measured in, watts and watt-hours. Power is defined as the rate at which work gets done. To figure out how much power you've got in a circuit, you multiply voltage by current. Your answer is given in units called watts. 1 watt is how much power is produced when 1 volt causes 1 amp of current to flow. Another unit you might hear mentioned is a kilowatt. That's 1,000 watts of power. Most electrical devices are rated for both voltage and power. For instance, the power rating on this light bulb tells you how much electrical energy the bulb converts into other forms of energy, like heat and light. The ratings are important. Anytime a device consumes more power than it's rated for, the device overheats. That excessive heat causes lots of equipment failure. Before we talk about energy in watt hours, I'm going to say it one more time. Don't ignore ratings. Now, what's a watt hour? Well, it's a measure of electrical energy. To get watt hours, you multiply power by time. A watt hour is the amount of energy used when 1 watt of power is delivered to a device for 1 hour. But a watt hour isn't a heck of a lot of energy. You'll be dealing in terms of kilowatt hours most of the time. A kilowatt hour, or kWh, is equal to 1,000 watt hours. Electric utilities use kilowatt hours to determine how much energy the customer uses, and they bill accordingly. What you pay is based on what you use. Well, that covers what we want to say about quantities and their basic units of measurement. Make sure everything we said regarding Ohm's law and how it works is absolutely clear. It's the key to understanding how everything in a circuit works.